An elementary course in Synthetic Projective Geometry by Derek Norman Lehmer. Chapter 9 continued. Section 152, Discovery of the Foci of the Conic. Section 153, The Circle and the Parabola. Section 154, Focal Properties of Conics. Section 155, Case of the Parabola. Section 156, Parabolic Reflector. Section 157, Directrix, Principal Axis, Vertex. Section 158, Another definition of a conic. Section 159, Eccentricity. Section 160, Sum or difference of focal distances. Problems. Section 152, Discovery of the foci of the conic. We know that on one axis no such points as we are seeking can lie. Section 150. The involution of points PP' on this axis can therefore have no double points. Nevertheless, let PP' and RR' be two pairs of conjugate points on this axis. Figure 43. Then we know that P and P' are separated from each other by R and R'. Section 143. Draw a circle on PP' as a diameter, and one on RR' as a diameter. These must intersect in 2 points F and F', and since the center of the conic is the center of the involution, PP', RR', as is easily seen, it follows that F and F' are on the other axis of the conic. Moreover, FR and FR' are conjugate normal rays, since RFR' is inscribed in a semicircle, and the two rays go one through R and the other through R'. The involution of the points PP', RR', therefore projects to the 2 points F and F' in 2 pencils of rays in involution, which have for corresponding rays conjugate normals to the conic. We may then say, there are 2 and only 2 points in the plane where the involution determined by the conic is circular. These 2 points lie on one of the axes, at equal distances from the center, on the inside of the conic. These points are called the foci of the conic. Section 153, The Circle and the Parabola. The above discussion applies only to the central conics, apart from the circle. In the circle, the 2 foci fall together at the center. In the case of the parabola, that part of the investigation which proves the existence of 2 foci on one of the axes will not hold, as we have but one axis. It is seen, however, that as P moves to infinity, carrying the line Q with it, Q becomes the line at infinity, which for the parabola is a tangent line. Its pole, Q, is thus at infinity, and also the point P', so that P and P' fall together at infinity, and therefore one focus of the parabola is at infinity. There must therefore be another, so that a parabola has one and only one focus in the finite part of the plane. Section 154, Focal Properties of Conics. We proceed to develop some theorems which will exhibit the importance of these points in the theory of the conic section. Draw a tangent to the conic and also the normal at the point of contact. These 2 lines are clearly conjugate normals. The 2 points T and N, therefore, where they meet the axis which contains the foci, are corresponding points in the involution considered above, and are therefore harmonic conjugates with respect to the foci. Figure 44. And if we join them to the point P, we shall obtain 4 harmonic lines, but 2 of them are at right angles to each other, and so the others make equal angles with them. Problem 4 of Chapter 2. Therefore, the lines joining a point on the conic to the foci make equal angles with their tangent. It follows that rays from a source of light at one focus are reflected by an ellipse to the other. Section 155. In the case of the parabola, where one of the foci must be considered to be at infinity in the direction of the diameter, we have A diameter makes the same angle with the tangent at its extremity as that tangent does with the line from its point of contact to the focus. Figure 45. Section 156. This last theorem is the basis for the construction of the parabola reflector. A ray of light from the focus is reflected from such a reflector in the direction parallel to the axis of the reflector. Section 157. Directrix. Principal axis, vertex. The polar of the focus with respect to the conic is called the directrix. The axis which contains the foci is called the principal axis, and the intersection of the axis with the curve is called the vertex of the curve. The directrix is at right angles to the principal axis. In a parabola, the vertex is equally distant from the focus and the directrix. These 3 points and the point at infinity on the axis being 4 harmonic points. In the ellipse, the vertex is nearer to the focus than it is to the directrix for the same reason, and in the hyperbola it is farther from the focus than it is from the directrix. Section 158. Another definition of a conic. Let P be any point on the directrix through which a line is drawn, meeting the conic at the points A and B, figure 46. Let the tangents at A and B meet in T and call the focus F. Then TF and PF are conjugate lines, and as they pass through a focus, they must be at right angles to each other. Let TF meet AB in C, then PACB are 4 harmonic points. Project these 4 points parallel to TF upon the directrix, and we then get the 4 harmonic points P, M, Q, N. Since now TFP is a right angle, the angles MFQ and NFQ are equal, as well as angles AFC and BFC. Therefore, the triangles MAF and NFB are similar, and FA is to AM as FB is to BN. Dropping perpendiculars AA' and BB' upon the directrix, this becomes FA is to AA' equal FB is to BB'. We have thus the property often taken as the definition of a conic. The ratio of the distances from a point on the conic to the focus and the directrix is constant. Section 159. Eccentricity. By taking the point at the vertex of the conic, we note that this ratio is less than unity for the ellipse and greater than unity for a hyperbola, and equal to unity for the parabola. This ratio is called the eccentricity. Section 160. Sum or difference of focal distances. The ellipse and the hyperbola have 2 foci and 2 directrices. The eccentricity, of course, is the same for one focus as for the other, since the curve is symmetrical with respect to both. If the distances from a point on a conic to the 2 foci are r and r', and the distances from the same point to the corresponding directrices are d and d', figure 47, we have r is to d as r' is to d', as r plus r' is to d plus d', as r minus r' is to d minus d'. In the ellipse, d plus d' is constant, being the distance between the directrices. In the hyperbola, this distance is d minus d'. It follows, figure 48, that in the ellipse, the sum of the focal distances of any point on the curve is constant, and in the hyperbola, the difference between the focal distances is constant. Problems. 1. Construct the axis of a parabola given 4 tangents. 2. Given 2 conjugate lines at right angles to each other, and let them meet the axis, which has no foci on it, in the points A and B. The circle on AB as diameter will pass through the foci of the conic. 3. Given the axes of a conic in position and also a tangent with its point of contact to construct the foci and determine the length of the axes. 4. Given the tangent at the vertex of a parabola and two other tangents to find the focus. 5. The locus of the center of a circle touching two given circles is a conic with the centers of the given circles for its foci. 6. Given the axis of a parabola and a tangent with its point of contact to find the focus. 7. The locus of the center of a circle which touches a given line and a given circle consists of two parabolas. 8. Let f and f' be the foci of an ellipse and P any point on it. Produce Fp to G, making Pg equal to Pf'. Find the locus of G. 9. If the points G of a circle be folded over upon a point F, the creases will all be tangent to a conic. If F is within the circle, the conic will be an ellipse. If F is without the circle, the conic will be a hyperbola. 10. If the points G in the last example be taken on a straight line, the locus is a parabola. 11. Finding the foci and the length of the principal axis of the conics in problems 9 and 10. 12. In problem 10, a correspondence is set up between straight lines and parabolas. As there is a fourfold infinity of parabolas in the plane and only a twofold infinity of straight lines, there must be some restriction on the parabolas obtained by this method. Find and explain this restriction. 13. State and explain the similar problem for problem 9. 14. The last four problems are a study of the consequences of the following transformation. A point O is fixed in the plane. Then to any point P is made to correspond the line P at right angles to OP and bisecting it. In this correspondence, what happens to P when P moves along a straight line? What corresponds to the theorem that two lines have only one point in common? What to the theorem that the angle sum of a triangle is two right angles, etc.? An elementary course in synthetic projective geometry. This book was written by Derek Norman Lehmer, Assistant Professor of Mathematics, University of California. It was published by Ginn and Company, Boston, 1917, and is now in the public domain. The text is available for free download at Project Gutenberg, read by Jim Renholt. Programming and illustrations by Jim Renholt, 2020. Corrections and comments are appreciated. Thank you for listening.